Hey folks, welcome to class 41. There's a lot of writing in this class, so I'm not going to be writing it live. I'm just going to be kind of talking through what was written during class. This might be slightly different than what was written during your class because every class I vary it just ever so slightly, but it should be more or less the same. So our goal for class 41 is to explain that a net force is required to move an object in a circular path and identify agent and direction of centripetal force. Identify directions of tangential velocity and centripetal acceleration. So the first thing we did is we wrote down Newton's first and second laws. So Newton's first law, this is abbreviated a bit, but it says that an object in motion will remain in motion at constant velocity in a straight line unless acted upon by a net force. And Newton's second law tells us that acceleration is equal to the net force divided by mass. So there's a quick little video here. Just check that out again. Does a really good job depicting it. If you recall, in class, it was a bowling ball rolling along the floor, and a sledgehammer was used to hit the ball in a circular path. When the ball was no longer hit with a sledgehammer, it then continued to move in a straight line path. So I am going to refer to this as a marble and a pencil because that was a thing I used to do in class where students would do similar simulation, but just using a marble and a pencil. But bowling ball, sledgehammer, same deal. It's analogous. All right. So it said once the ball enters the circle at point one, by the way, that's referring to this diagram on the back page. So once the ball, once the ball enters the circle at point one, how can you use the pencil to keep the ball moving in a circle, or in this case, the sledgehammer? And you'll notice in the video, he hit the ball toward the middle of the circle. Now it says if you stop hitting the marble with the pencil, so when he stopped hitting the bowling ball with a sledgehammer, what happens to the bowling ball? Be specific with direction. It went in a straight line, okay? And even more specific, I didn't even write it here, but it went in a straight line tangent to the circle. All right. Now, if Newton's first law, use Newton's first law to explain why you must apply a force toward the middle of the circle to keep an object moving in a circle or any curved path. So it says here, objects want to move in straight lines. That's basically what Newton's first law says. To move an object in a curved path or a curved line, a net force must be applied. All right. So looking at that diagram on the back page, let's draw velocity and force vectors at those instants 1, 2, 3, and 4. So if it were moving in a counterclockwise circle, velocity would always point tangent to the circle in a straight line, and the force of the hammer would always point towards the middle of the circle. The next one says, what do you notice about the direction of the velocity as the ball moves around its circular path? If you look at that picture, the direction of the velocity changes. At one point it's pointing up, then it's pointing left, down, right. It's always pointing in a different direction, but the magnitude of it doesn't change. So if the direction of the velocity changes, then the velocity changes. If the velocity changes, we call that acceleration. The object is accelerating. So just because the size of the velocity isn't changing doesn't mean the velocity is not changing. If the direction's changing, it's accelerating. So how can Newton's second law be used to explain an object moving in a circle must have a net force acting on it? Well, Newton's second law is A equals F net over M. If an object is changing direction, it must be accelerating. And we know that accelerations require a net force according to Newton's second law. Here's an excellent video. Watch it again about centripetal force and centripetal acceleration. So centripetal force is the net force that keeps an object moving in a circle, and it always points toward the middle of the circle. Centripetal acceleration is the acceleration of an object moving in a circle. Below, what do you notice about the directions of the velocity in the centripetal acceleration? Hopefully you notice in this picture here, the directions of the velocity and the centripetal acceleration are always changing. Velocity is tangent to the circle, acceleration is toward the middle, but the magnitudes of those numbers are constant. Number 11 says, if an object is moving in a curved path, it must have a force, specifically a centripetal force, acting on it. But the centripetal force in and of itself isn't enough information to tell us what the force is. There is always an agent of the centripetal force, something that causes the centripetal force. For example, in the image above, the tracks keep and push the roller coaster carts in a circle. In the simulation we saw earlier, or excuse me, in the video, it was the sledgehammer that provided the force. if I whirl a ball on a string, it's the tension of the string or the force of the string that provides that centripetal force. So there has to be an agent of the centripetal force for something to move in a circle. Excuse me. So this one here says draw the circular path of the ball on the string in the space below. So here's a ball on a string at two different positions. The velocity is always tangent to the circle, and the centripetal forces and accelerations are always pointing toward the middle. There's no words for there for I. Using Newton's first law, explain why the direction of the ball, excuse me, using Newton's first law, explain which direction the ball would go if the rope snapped. Draw this in the picture above. I actually drew it in a picture to the right. So the ball would travel in a straight line tangent to the circle because there is no more centripetal force keeping it in a circle. So for example, if a ball were going in a circle, pretend it's like a top-down view and I'm swinging it above my head. If a ball were going in a circle and the string snapped, the ball would travel in a straight line tangent to the circle. We kind of voted on it, but it would be path 2, the direction of the velocity at that point. So here's another example. A car is traveling around a circular bend. It hits a patch of ice. So you got the car going around. Here it is, and it hits a patch of ice right here. What direction would the car go? It's going to go in a straight line tangent to the circle. Therefore, what is the agent of the centripetal force that keeps the car moving in circular paths, and how can you tell? It's friction. Friction is what keeps cars moving in a circle. Without it, they leave the circle. Think about when you hit the patch of ice. The reason you skid out and go in a straight line is because there is no more friction to keep you moving in a circle. The agent of the centripetal force has disappeared. So there's nothing to keep you in a circle. So this question here is if the sun's gravity suddenly disappeared, in which direction would the Earth go? So here's the Earth going around the sun. We have choices 1, straight line tangent, 2, stays in the curved path, 3, straight line outward, and 4, maybe it just stops moving. It would go in path or choice number 1 here. It would go in a straight line tangent to the circle, kind of sticking with the theme. Therefore, what is the agent of the centripetal force that keeps all celestial bodies in nearly circular orbits? It's the force of gravity. Without gravity, objects don't move in circles in space, roughly circles. So this question here says an object is moving at constant speed in a circular path. The object's centripetal acceleration remains constant in, what remains constant? The centripetal acceleration, remember, always points towards the middle of the circle. But the middle of the circle is always in a different place depending on where the object is going around the circle. So it's pointing towards the middle, which is changing. So the magnitude of the centripetal force doesn't, actually, the centripetal acceleration and force doesn't change, but the direction is always changing. All right. Then this question here is just a little image. Centripetal force points to acceleration, points towards the middle, and the tangential velocity is always tangent to the circle. All right. So centripetal acceleration always points towards the middle, velocity always tangent to the circle. And there we have it.